In this day of notes, we're going to take a little bit more look at rational functions, and we're going to do basically two things with these notes. The first part of today's notes, we're going to look at how to find the equation of a rational function if somebody gives you information about what kind of vertical asymptotes or horizontal asymptotes or removable discontinuities that they'd like it to have. And the second part of today's notes, we're going to talk about how to make a graph of a rational function by hand. As we've already seen, using the graphing calculator sometimes doesn't show us all the details about what we'd like to see in our rational function. So it's oftentimes better if we just do it by hand. So anyways, let's go back to the first part. So the first part of today's lesson is going to be finding equations of rational functions using information that's given to us about the different kinds of asymptotes and removable discontinuities that it needs to have. So the first thing is, whenever you're given information about these, they're going to tell you about like one part of your formula. Use the vertical asymptotes to determine any factors of the denominator. So let's say, for example, if somebody says that a vertical asymptote is x equals 5, that means in the bottom part of your fraction, there has to be a factor that produces x equals 5 as a 0, so that would be x minus 5. So vertical asymptotes directly relate to factors that are going to appear in your denominator. Number 2, use any removable discontinuities to determine factors that are going to appear in both the top and bottom part of the fraction. So if somebody tells you about a removable discontinuity, let's say they tell you a removable discontinuity is x equals -3, that means when we go to make our polynomial on top and bottom, both of them would have to have x plus 3 as a factor. So remember, removable discontinuities are the answers to the factors that would cancel. So if x equals -3 is a removable discontinuity, that means that x plus 3 must have been showing up on both the top and the bottom. And last part is use any horizontal asymptotes to determine the degree of the numerator in relationship to the denominator. So again, what we're doing with the horizontal asymptote is a comparison of who's got the bigger degree. If they tell you that there is no horizontal asymptote, that means you know the top part has a bigger degree. So you'd have to multiply by enough x's or enough terms that have x's in them in order to make sure the top is bigger than the bottom. If they say that y equals 0 is the horizontal asymptote, then you know that the bottom has the bigger degree. And again, you'd have to make sure that that happens that way. And last but not least, if you have a horizontal asymptote that's y equals any other number other than 0, that means the top and the bottom had the same highest power of x, and the number that y is equal to would be the ratio of the leading coefficients between the numerator and the denominator. So let's take a look at a couple of examples of how to create the equation of a rational function using the given information. So in this particular problem, they're telling us our vertical asymptote is 3, our removable discontinuity is x equals -2, and that the horizontal asymptote that there isn't one. So I'm going to start building my polynomial function. First, I'm going to use the vertical asymptote of x equals 3 to recognize that the denominator must have a factor of x minus 3. Vertical asymptotes tell you about what's in the denominator. Second, removable discontinuities are going to be factors that show up in both the top and the bottom. So if I have x equals -2 is a removable discontinuity, that means that x plus 2 is going to have to show up in both the top and bottom part of this fraction, because removable discontinuities are factors that reduce. And last but not least, it says I have a horizontal asymptote of none. This only happens when the numerator's degree is greater than the denominator's degree. So in other words, there's more x's in the top part of the fraction. Now currently, with the setup that I have, when I multiply the bottom part of the fraction, first, outer, inner, last, I'm going to get x squared minus x minus 6. And in the top part of the fraction, I don't have that many x's yet. So what that means is I'm going to have to multiply the numerator by enough x's to make it have a bigger degree. In other words, since I have a degree of 2 in the bottom and currently only have a degree of 1 in the top, I'm going to have to multiply by at least 2 more x's. So I'm now going to distribute this x squared through the parentheses to give me x cubed plus 2x squared in my numerator. This is not the only example, but this is one example of a rational function that would produce the kinds of vertical asymptotes, removable discontinuities, and horizontal asymptotes that they were looking for in this particular problem. All right, let's try one more example like this. Find the equation of a rational function with removable discontinuities at plus and minus 2. Vertical asymptotes at x equals plus and minus 2, removable discontinuities, none, and a horizontal asymptote of y equals negative 3. So again, I'm going to start this thing off. Remember, they're always functions built on a fraction. So the fact that the vertical asymptotes are x equals plus and minus 2 means that the factors were going to be x plus 2 and x minus 2. Those both need to go only in the denominator, which when you multiply them together is going to be x squared minus 4. Removable discontinuities, none. What that means is there are no factors that are going to appear on both top and bottom. And then for horizontal asymptote, they want it to be y equals negative 3. This means the only way that you get a horizontal asymptote of y equals negative 3 is that you have to have the same degree in the numerator and denominator, and the ratio of leading coefficients is 3:1. So as you can already see, I'm getting a quadratic in my denominator because of the two factors that make my vertical asymptotes. So that means I'm going to have a quadratic in the numerator as well. And in order for the ratio of the leading coefficients to turn out to be 3:1, my numerator is going to have a 3 in front of that x squared. So this is an example of a formula that I could use that would produce all of the information that they wanted. Vertical asymptotes at plus and minus 2, and also a horizontal asymptote of, negative 3. This needs to be a ratio of negative 3. I forgot about the negative. So negative 3:1. Y equals negative 3. Okay. The last thing that we're going to do today is we're going to talk about how to draw the graph of a rational function by hand. So the first thing that you're going to want to do when they give you your rational function is you're going to want to find the y-intercept. The way that you always find a y-intercept is you plug x equals 0 into the formula. So in other words, you evaluate at x equals 0. To find the x-intercepts, you're going to want to find the zeros of the numerator. So whatever numbers makes the top part of your fraction go to 0. Because remember, 0 divided by anything is 0. So really, we want to just focus on the numerator for coming up with the zeros. Step number 3 is going to be determine if there are any factors that reduce, therefore producing removable discontinuities. So we want to factor the top and factor the bottom and see if any of the factors cancel out. If there are factors that cancel out, those are going to tell you about your removable discontinuities like we've practiced. And remember, those would be the holes in the graph. Number 4, you want to find any vertical asymptotes and horizontal asymptotes and draw them on the graph as dotted lines. So after you've checked to see if anything reduces, anything left over that still makes your denominator go to 0 is going to be a vertical asymptote, and horizontal asymptotes are found by comparing who's got the bigger degree on top or on bottom. And those are actually not part of your graph, but they're very helpful in making the graph. So you're going to want to draw them as dotted lines. They're not actually part of your function, but they're there to help you draw your function. The 5th step that I want you to do is to make an x and y chart, and you're going to want to pick x values from both sides of any vertical asymptotes that you have. So if you have, like, let's say a vertical asymptote at x equals -1, you're going to want to pick some numbers that are smaller than -1 and also pick some numbers that are bigger than -1 so you can see what's happening on both sides of the asymptote. Once you've picked those numbers in the x column, you have to find the y values that go with them in the right-hand column. So 6th and final step, you're going to make a graph that goes through all the points that are in your chart and then also approach any asymptotes that you have drawn on your picture. So People oftentimes will ask, how many points do I need in my chart? There is no pre-specified number of points that you need in your chart. I would say it this way: you need enough points in your chart to understand how the graph is approaching your asymptotes. And the minute that you do, the minute that you're like, oh, I see how this is going, I see how this is going to get closer to those lines, then you've got enough points. But make sure you're doing that on both sides of any vertical asymptotes. Don't forget to show the holes at any locations that were your removable discontinuities. Don't make the same mistake that your graphing calculators make. So if there's a removable discontinuity, you got to remember to go back and put a hole in your graph at those spots. All right, so let's give this a try. We're going to get, over the next couple of days, we're going to get a lot more practice with this. This is not going to be our only day graphing. So you're only going to see me do one example today, but we'll do a lot more tomorrow. So example number one, graph the following function, f of x equals 2x squared minus 5x plus 2, all divided by x squared minus 2x. So the very first thing that you want to do is you want to find your y-intercept. And the way that you do that is by plugging a 0 into your formula everywhere for x. So 2 times 0 squared minus 5 times 0 plus 2 gives me a 2 in the numerator. And when you put a 0 in everywhere in the denominator, you get 0. So the y-intercept is 2 divided by 0, which is undefined, which means this particular graph does not have a y-intercept. In other words, the graph never actually crosses the y-axis. And for a second, you might wonder, how can that happen? But what that probably means is that the y-axis happens to be a vertical asymptote in this problem. And we'll see. All right, x-intercepts. X-intercepts are found by setting your numerator equal to 0. So you're going to want to take that 2x squared minus 5x plus 2 and set that equal to 0. You want to factor it if you can, which this is actually going to break into 2x and 2x. I'm sorry, 2x and 1x. And two numbers that multiply together to make positive 2 in a arrangement that would allow the middle term to make negative 5 would be if I put the minus 2 behind the regular x and the minus 1 right here. If you don't believe me on this, go ahead and multiply that back together, and you will realize that those two factors do in fact produce a middle coefficient of negative 5. So if these are my two factors, that means one of my answers is 1/2 and the other answer is 2. So as I start to draw this, I already know that one place I'll be hitting the x-axis is here at 1/2, and the other place is here at positive 2. Okay, so the next thing we want to do is we want to see if there's any removable discontinuities. Okay, so we've already factored the top part. We realized that this factors into 2x minus 1, and then there was another factor of x minus 2. And if I factor the bottom part of this fraction, we get x times x minus 2. And so we realize that x equals 2 actually is no longer an x-intercept anymore. Let me get rid of that. What we realize is that x equals 2 is actually a removable discontinuity. In other words, when we get to an x value of 2, wherever the graph happens to be at that place, it's a factor that cancels from the top and bottom. So wherever the graph is at that point, there's a hole in it. So there is no graph at x equals 2. Now let's talk about vertical asymptotes. After the reducing of this fraction, we notice that the only thing left in the bottom is x. So that means the vertical asymptote is going to be at x equals 0. X equals 0 is just a fancy name for your y-axis. So this is, again, why my graph never hits the y-axis, because it's a vertical asymptote. And then let's talk about horizontal asymptotes. At this point, after I've reduced, the only part of this that's left is linear on top and linear on bottom. In other words, we have the same highest power of x in both the top and the bottom, and the ratio of the leading coefficients is 2 to 1. So my horizontal asymptote for this is y equals 2. So on my graph, at a y value of 2, I'm going to draw a horizontal line across my paper. Don't forget to label these asymptotes. Y equals 2, x equals 0. These lines are not actually part of my graph, but they're there to guide you in making a better looking graph. Now, the last thing that you're going to want to do here is you're going to want to make an x and y chart, and you want to pick some x and y values. You want to pick some x values from both sides of your vertical asymptote. My vertical asymptote in this problem is x equals 0. Don't put 0 itself in there because you already know you cannot use 0 because it's going to make the denominator go to 0. But you can pick some numbers that are smaller than 0, and you can pick some numbers that are bigger than 0, and go ahead and plug those into your formula. Now at this point, we actually, because there was a removable discontinuity, you can make your life a little bit easier and plug it into the reduced formula, which is the one that I have circled up here. So if I put a -2 into the numerator, you're going to get -4 minus 1 more, which makes -5. And you're dividing by -2 on the bottom. So that makes 2.5. If you put a -1 into the numerator, you're going to get -1 times 2, which is -2 minus 1 more makes -3. And so you're going to get -3 over -1, which is 3. So on the left side of this, if I start plotting where I'm at -2, you're at 2.5, about here. At -1, you're at 3. So if I have to get close to the horizontal dotted line, and I have to get close to the vertical dotted line, and I have to go through these two dots that I've already drawn in order to do it, then my graph is going to look like this. For +1 and +2, if I plug those values into my reduced formula, 2 times 1 is 2 minus 1 makes 1 over 1. So when x is 1, y is 1. And if I put a 2 into the formula, 2 times 2 is 4, minus 1 makes 3, divided by 2 is going to be 3/2. So at an x value of 2, I'm at 1.5. Now don't forget, you not only have these 2 points that I just plotted from my chart, but we also have our x-intercept. And I'm going to go ahead and draw this graph in. Okay, you've got to label your equation with the equation that you had originally, which was 2x squared minus 5x plus 2, all divided by x squared minus 2x. And one last thing, hopefully you haven't forgotten about this, we did have a removable discontinuity at x equals 2. So wherever our graph was at an x value of 2, there's a hole in it. So go back, erase that spot of the graph, and put a hole in it. This is something that your calculator will not show you, and this is why it's preferable to graph these by hand. If you did this on the graphing calculator, you would see in the table that there's an error at an x value of 2. So even though this is what my reduced formula says that it should be at an x value of 2, we remember that the original formula would have had a removable discontinuity at 2, so we really shouldn't be using it. That's going to be a hole in the graph. Okay, so we're going to get some more practice with graphing these rational functions in the future. Actually, that'll be more tomorrow. But try the homework that I've given you for tonight.